Convolutional neural networks, commonly abbreviated as CNNs, are one of the most influential architectural innovations in modern artificial intelligence, especially in domains involving spatially structured data such as images, video, and certain types of audio. To understand why CNNs became so dominant, it helps to begin with the limitations of earlier neural network designs and the specific statistical structure of visual data. Traditional fully connected neural networks treat every input feature as independent and equally related to every neuron in the next layer. If you feed an image into a fully connected network, the model must learn from scratch that nearby pixels tend to be correlated, that edges are local phenomena, and that patterns repeat across different parts of the image. This is extremely inefficient both statistically and computationally. CNNs were designed specifically to encode useful inductive biases about spatial locality and translation invariance directly into the architecture. The key conceptual shift in convolutional neural networks is weight sharing through convolutional filters. Instead of connecting every input pixel to every neuron, a CNN applies small learnable filters that slide across the spatial dimensions of the input. Each filter looks at a local receptive field and produces a feature map indicating where that pattern appears. This dramatically reduces the number of parameters while simultaneously improving generalization. At a mathematical level, the convolution operation used in CNNs is actually closer to cross-correlation as implemented in most deep learning libraries, but the terminology from signal processing has remained. A filter, often called a kernel, is a small matrix of learnable weights. As it moves across the input image, it computes a dot product between the kernel and the local patch of pixels. The result is written into the corresponding position of the output feature map. One of the most important consequences of this design is translation equivariance. If a feature in the input image shifts slightly, the activation in the feature map shifts correspondingly rather than changing arbitrarily. This property aligns well with natural images, where objects can appear in different positions but retain the same identity. Fully connected networks do not naturally possess this property. Another critical advantage is parameter efficiency. Consider a modest grayscale image of size 224 by 224 pixels. A fully connected layer with even a small hidden layer would require tens of millions of parameters. A convolutional layer using a 3x3 kernel and dozens of channels requires orders of magnitude fewer parameters. This reduction not only improves memory efficiency but also reduces overfitting risk when data is limited. A typical convolutional neural network is composed of several types of layers arranged in sequence. The most fundamental is the convolutional layer itself. This is usually followed by a nonlinear activation function such as ReLU, which introduces nonlinearity and allows the network to approximate complex functions. Periodically, pooling layers are inserted to reduce spatial resolution and increase the receptive field of deeper neurons. Pooling layers perform a form of downsampling. The most common version is max pooling, which takes the maximum value within a small window, such as 2 by 2. The intuition is that the exact position of a feature within that small region is less important than whether it exists at all. Pooling contributes to a degree of translation invariance and reduces computational cost by shrinking feature maps. However, pooling is not without controversy. Some modern architectures reduce or eliminate pooling in favor of strided convolutions, which perform learned downsampling. The trade-off involves considerations of information preservation, aliasing, and architectural simplicity. Understanding when to use pooling versus strided convolution remains an active design consideration. As we move deeper into a CNN, the receptive field of each neuron grows. Early layers typically learn simple, local features such as edges, corners, and color contrasts. Intermediate layers combine these into more complex motifs like textures and object parts. Deep layers often represent high-level semantic concepts such as object categories. This hierarchical feature learning is one of the central strengths of convolutional architectures. The concept of the receptive field deserves careful attention. In early layers, a neuron sees only a small patch of the original image. But as layers stack and pooling reduces spatial dimensions, the effective receptive field expands. Theoretical receptive field size can be computed exactly from kernel sizes and strides, but in practice the effective receptive field tends to be smaller and Gaussian-like due to optimization dynamics. Another key design dimension in CNNs is the number of channels, sometimes called depth. Each convolutional layer typically produces multiple feature maps, each corresponding to a different learned filter. Increasing channel count increases representational capacity but also increases compute and memory cost. Architectural design often involves balancing spatial resolution against channel depth. Padding is another technical detail that has significant consequences. Without padding, convolution reduces spatial dimensions at each layer. Zero padding allows the output to maintain the same spatial size as the input when desired. Padding choices affect boundary behavior, information preservation, and alignment of feature maps across layers. Stride controls how far the convolutional kernel moves at each step. A stride of 1 produces dense coverage, while larger strides downsample the feature map. Stride therefore interacts closely with pooling and overall network resolution. Aggressive early downsampling can reduce compute but may discard fine spatial detail important for tasks like detection or segmentation. From an optimization perspective, CNNs are trained using the same gradient-based methods as other neural networks. Backpropagation computes gradients of the loss with respect to each filter weight, and stochastic gradient descent or its variants update the parameters. However, the structured parameter sharing in CNNs leads to different gradient statistics compared to fully connected networks, which can influence learning rate choices and initialization strategies. Initialization is particularly important in deep CNNs. Poor initialization can lead to vanishing or exploding activations across layers. Modern practice typically uses variants of initialization for ReLU-based networks, ensuring that variance is preserved through the forward pass. Batch normalization is also widely used to stabilize training by normalizing intermediate activations. Batch normalization layers normalize each channel's activations across the batch and spatial dimensions, then apply learnable scale and shift parameters. This helps reduce internal covariate shift and allows for higher learning rates. However, batch normalization introduces dependencies between examples in a batch and behaves differently at training and inference time, which can complicate deployment. Regularization techniques are also crucial in CNN training. Data augmentation is particularly powerful in vision tasks. By randomly flipping, cropping, rotating, or color jittering images, the effective training dataset is expanded, and the model becomes more robust to natural variations. Dropout is sometimes used in fully connected layers of CNNs, though it is less common in convolutional blocks in modern architectures. Historically, one of the breakthroughs that brought CNNs to prominence was their success on large-scale image classification benchmarks. Early architectures demonstrated that deep convolutional models trained on sufficiently large datasets could dramatically outperform traditional computer vision pipelines based on hand-engineered features. As CNN architectures evolved, several design patterns emerged. One trend was increasing depth while controlling parameter growth. Another was the use of smaller kernels stacked in sequence rather than large kernels. For example, 2 consecutive 3x3 convolutions can approximate the receptive field of a 5x5 convolution with fewer parameters and more nonlinearities. Residual connections were another major innovation. In very deep networks, optimization becomes difficult due to vanishing gradients and degradation problems. Residual blocks introduce skip connections that allow gradients to flow more directly through the network. This enables successful training of networks with hundreds of layers and has become a standard architectural component. Another important development is the concept of bottleneck layers. Instead of using wide convolutional layers everywhere, bottleneck structures compress the channel dimension using 1x1 convolutions, perform computation in a lower dimensional space, and then expand back. This improves computational efficiency while preserving representational power. Global average pooling is often used near the end of modern CNNs to replace large, fully connected layers. Instead of flattening the feature map, the network averages each channel spatially, producing one value per channel. This reduces parameter count and encourages the network to maintain spatially distributed evidence for each class. While CNNs originated in image processing, their principles extend to other modalities. In audio, One-dimensional convolutions operate over time. In video, three-dimensional convolutions capture spatiotemporal structure. Even some natural language processing models have historically used convolutions over token sequences, although transformers have largely taken over in that domain. Despite their success, CNNs have known limitations. Standard convolutions have a limited receptive field relative to image size, especially in shallow networks. Capturing long-range dependencies can require deep stacks or large kernels. Attention mechanisms and vision transformers have been partly motivated by this limitation. Another limitation is sensitivity to geometric transformations outside the training distribution. While CNNs are translation equivariant, they are not inherently invariant to rotation, scale changes, or perspective shifts unless trained with appropriate augmentation or specialized architectures. Interpretability is also a nuanced topic. Feature visualization techniques can reveal that early CNN layers learn edge detectors and color blobs, which aligns with intuition. However, deeper layers often learn highly distributed and abstract representations that are harder to interpret cleanly. From a systems perspective, CNNs are computationally intensive but highly parallelizable. Convolution operations map well to GPUs and specialized accelerators because they involve regular, dense linear algebra patterns. Much of the practical progress in CNNs has depended not just on algorithmic advances but also on improvements in hardware and optimized libraries. Memory bandwidth and data movement are often the true bottlenecks in CNN inference, especially on edge devices. Techniques such as quantization, pruning, and weight compression are commonly used to deploy CNNs efficiently on mobile or embedded hardware. These optimizations attempt to preserve accuracy while reducing model size and compute. In modern AI systems, CNNs are frequently components within larger pipelines. For example, object detection systems use CNN backbones to extract features, followed by specialized heads for bounding box prediction. Semantic segmentation networks use encoder-decoder CNN structures to produce dense pixel-wise predictions. The convolutional backbone remains a central building block. The field continues to evolve. Hybrid architectures combining convolution and attention are increasingly common. Vision transformers challenge CNN dominance in some benchmarks, especially at very large scale. Nevertheless, CNNs remain extremely competitive, particularly in resource-constrained environments and tasks with strong spatial locality. For a technically sophisticated audience, the most important mental model is that CNNs succeed because they embed the right inductive biases for spatial data. Weight sharing encodes the assumption that patterns repeat across locations. Local connectivity encodes the assumption that nearby pixels interact more strongly than distant ones. Hierarchical stacking encodes the compositional structure of visual scenes. When those assumptions align with the data distribution, CNNs are extraordinarily effective. When the assumptions break down, alternative architectures may perform better. Understanding these inductive biases is more important than memorizing any specific architecture. In practice, designing and training effective convolutional neural networks requires careful attention to resolution schedules, channel scaling, normalization strategy, data augmentation, and optimization hyperparameters. Small architectural choices can have large downstream effects, especially in deep models. Ultimately, convolutional neural networks represent one of the clearest examples of how incorporating domain structure into neural architecture can transform performance. They are not magic, and they are not universally optimal, but they demonstrate the power of aligning model structure with the statistical geometry of the data. For anyone working seriously in AI systems, a deep intuitive and mathematical understanding of CNNs remains foundational knowledge.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.